Welcome to this video on the electric field part 5. In this video we're going to be taking a look at different cases of the electric field as a vector field, and we'll start with the challenge that I left you with at the end of the last video, was to figure out at this location right here what is the strength of the electric field, or how can you show that it's actually stronger than the field at either one of these spots over here. Okay, so what I'm going to do is I'm going to decide, on my structure. So I know that I'm only looking at it in the y dimension right here. So I'm going to say that at this location right here, that's a point, right? The electric field due to, we'll start with the blue charge, is pointing up like this. And the electric field due to the red charge is also pointing up. Now I know that because a positive charge, right, which is right here, has the electric field lines pointing away from it, and the blue charge has the electric fields pointing towards it because it's negative. So what I'm going to go ahead and do is, I guess let me label these again. We'll call this one Q1 and the electric field due to it E1. And then for the red one, we'll call this Q2 and the electric field E2. Now, with the electric field statements, what I'm going to say is at that location, right? Because that's the only spot we're looking at. So at that position, I'm going to say E2, right, is in the positive y direction. So I make sure that I say that E2 is positive. And then I see that E1 is also pointing in the positive direction at that location. So I'm going to say plus E1. And then I can show that those two values are equal to the E net at that particular point right there. So I can show that if both of these values are positive, E net is greater than just E1, which is also greater than just E2, because these have summed together. Now what I can show is I can actually expand this to include the whole electric field equation, which I know is 1 over 4 pi epsilon naught times q over r squared. Now, one thing that we didn't really look at before was the fact that the q is an absolute value. In other words, don't include the fact that this is negative and this is positive, because that will affect the outcome of the answer, and q is not a vector. E is a vector. So if you include the sign of Q, you will affect the sign of E, and that's not what would be indicative of what the electric field is necessarily doing at that place. So you can see that right here at this location, the field, they both point in the upward direction, right? But if we take a look at this, say we pick this point over here. So that point down there, if we were going to write the same statement, the net electric field for this point over here, what we would have to look at is, okay, due to the red charge, the field direction is down at that point, and due to this charge over here, or to this point over here, the field that's due to this one is still pointing upwards. So you can see that in this region right here, there's an opposite direction for the two. So when I write this, I can see E1 is positive because it's pointing in the positive y direction, but E2 is pointing in the negative y direction. So I would have to do plus negative E2, or just minus E2, and that equals E net at that point. Now, you might be thinking, well, wouldn't this just cancel out over here? Well, not necessarily, okay? And in fact, not in this case. So what I'm going to do is I'm going to expand this equation. So I'm going to say E1 is equal to, and I'm going to leave the constant way out front here, and I'm going to do Q1 over, and I'm going to put R squared, R1 squared, because it's the distance from Q1 to that point. Now, Q2, and I forgot I need to go ahead and make this, because I factored out my constant. So E2 at that point, I'm going to do minus Q2 over R2 squared, and that equals, go ahead and move this over a little bit, that all equals E net. Now, we can see at this green point right here that I selected to figure out the field at, the distance from Q1 is pretty big, right? But the distance from Q2, and I'll go ahead and do that also in green just so we can see it, that distance is a lot smaller. So we can see that this value, R1, is a lot greater than R2, right? And because of that, because it has an inverse relationship with the electric field, this is contributing a weaker amount of field, and this is contributing a stronger amount of field. So we see that at that location, if we were to figure out what the value of this, if it's going to be positive or negative, the net amount of field, we would say that the E net in this direction is going to be negative. And so that just means that it's going to be pointing down. And we see that actually with the arrow over here. So all these arrows in this picture are the net field directions. And that's why we would say that, okay, if this is, say, 2, and this number has to be bigger, so let's say it's 6, right? Then that's going to come up with a negative 4 value. Newtons per coulomb are the units. So you can see how that would work. Now, before we end this video, we're going to just take a look at one more scenario where I have 3 charges, and just to try to show here how this might, how we might analyze this situation. So I see that there are 3 positive charges, all with a value of q, and they're all separated by a distance a from one another. And let's say I want to figure out a location somewhere where the electric field would be 0. So I put them on our Cartesian plane, and you could, I haven't given you any numbers here, but I could say that, the distance this one is from this one, I have all those values. Everything's kind of planned out. So what I'm going to say is, where is the electric field 0? Somewhere right in between all of these. So what I'm going to do is I'm going to say, if I pick this point right here, let's go ahead and state the direction of the field at that point due to each of these charges. So what that means is draw the electric field lines, which you can imagine for positive charges are going to always point away from the charges. So I'll go ahead and do this just to help us visualize. We have all of these charges pointing away, and at this point right here, due to this charge, the field is pointing in the negative direction. Okay, we'll go ahead and make this one blue. Due to this charge, the electric field is pointing that direction, and we'll make this one green. Due to this field, the electric field is pointing in that direction, right? And so over here, at this point right here, if I wanted to figure out what the net electric field direction was, I could do so. So I could say, let's label these from each field. So I'll make this one E1. I'm going to go ahead and make this one E2, and the green one E3. Now they are all the same charge, and they're all the same distance to this point, and so I'm going to, I know that they'll all, E1, E2, and E3 will actually all be the same strength value, but I want to make sure that I can show that, so I'm just separating them out. So what I would do is I'd say E1 is all in the y, right? But E2 has some positive y value and some positive x value. E3 has some positive y value and some negative x value, right? So if I'm just adding up the y components, I would say E1 in the y, which is negative, right? Plus E3 in the y, which is positive because that component's pointing up, and then plus E2 in the y, which is also pointing up, and that's going to equal E net in the y. Now, I would do the same for the x dimension. So E1 in the x, that's 0 because it's pointing neither left nor right at all. It's just pointing straight down, so I'll leave that out. But I have that E2, right? E2 is a positive value, and I can see that E3 is a negative value, right? And because these are equidistant, I would say that basically what's happening is it's going to cancel itself out in that direction. And so I will end up with 0 in this direction. Now, if I look at these two over here, what I'm seeing in this scenario is that this actually might end up canceling out as well, and it may be a 0 value. Now, that's the challenge that I'm leaving you with for this video, is to figure out, does all of this actually sum up to 0 over here? And if so, how would that be possible? And if not, what would the total net value of this field actually be? And when we come back in the next video, we'll take a look at that, and then we'll move along.